Hello there, and welcome to the Drift to the Stars. I'm so glad you found your way here tonight. Wherever you are tucked beneath a blanket, lying in the dark, letting the day slowly release its hold on your shoulders, this is a space made for you. There is nothing you need to do here, nothing to solve, nothing to finish. Only this, a quiet hour, or two, or three, drifting gently through the most extraordinary place that has ever existed. And just before we begin, if these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, if you're ready, let's begin. Look up on a clear night, and you see something that seems simple. Stars, darkness, the familiar scatter of light that humans have watched since before they had words for what they were seeing. But the sky you are looking at is not a single moment. It is not a photograph taken all at once, the way you might imagine. Every point of light up there left its source at a different time, some thousands of years ago, some millions, some so long ago that the universe itself was barely recognizable. The star directly overhead might be showing you light that began its journey before your great-grandmother was born. The one beside it might be sending you a message from an era when woolly mammoths still walked the earth. You are not looking at the sky as it is. You are looking at the sky as it was layered, ancient, a mosaic of different pasts assembled into one quiet picture above your head. Astronomers call this look-back time, and it means the night sky is less like a window and more like a museum. Every glance upward is a journey through history that requires no ticket, no travel, no effort at all, only the willingness to look. The sky remembers things we have long forgotten, and it offers them back, gently, every night. There is a star you could not see it with your eyes alone called UY Scuti. If you placed it where our sun sits, its surface would extend past Jupiter. Not to Jupiter, past it. A sphere so wide that if you tried to drive around its equator at highway speed, the journey would take more than 1,000 years. Our entire solar system, every planet, every moon, every comet looping its long elliptical path, would be swallowed inside it with room to spare. And yet, from Earth, it appears as nothing more than a faint smudge of red near the center of the galaxy, unremarkable against the crowd. Size, out there, does not announce itself. The cosmos keeps its largest secrets in plain sight, waiting for those patient enough to measure twice. What this means is not that we are small, though we are, of course. We are. But that smallness carries no shame in a universe where even the largest things drift quietly without fanfare. The star does not know it is enormous. It simply burns, slowly, turning itself into light and heat, and eventually, in its own time, into the seeds of something new. Something new that might already be inside you. Not metaphorically, literally. The atoms that make up your bones, your blood, the soft tissue of your hands resting wherever they rest right now, most of them were not made here. They were not made on Earth, or even in this solar system. They were forged in the cores of stars that lived entire lifetimes before our sun existed. Stars that burned for millions of years, collapsed, and then exploded, scattering their contents across the galaxy like slow, silent breath. That scattered material drifted through interstellar space, gathered into new clouds, collapsed again, and eventually, through a process so long and so indirect, it almost defies following, became part of a planet, part of an ocean, part of a living thing, part of you. The iron in your blood was made in a stellar explosion. The calcium in your bones was fused in a star's final hours. You did not come from the Earth in any final sense. You came from much further away than that, and much longer ago. You are, in the most precise and honest way that science allows, made of stars. Not poetically, actually, right now, as you breathe, a relationship is happening that you cannot feel. The light warming your room, or the darkness cooling it, is not current. 8 minutes ago, that light was still inside the sun. It had just completed a journey through the sun's interior that took, in some cases, tens of thousands of years, slowly bouncing from particle to particle in the dense solar core before finally escaping. And then it crossed the distance between the sun and the Earth in just over 8 minutes, 150 million kilometers, traveled in the time it might take you to make a cup of tea. What this means is quietly strange. You have never seen the sun as it is right now. No one has. No one can. The sun you see is always slightly in the past, always a few minutes behind itself, always the version that existed before this moment. In a universe where we often assume we are seeing what is there, the sun reminds us that all perception is delayed, that all light is a letter already sent, arriving after the moment it was written. Letters that were written under conditions almost unimaginable, like those inside a neutron star, where the laws of physics seem to lean against each other in ways that strain description. When a massive star dies, its core can collapse so completely that protons and electrons are crushed together into neutrons, forming an object no larger than a city, but containing more mass than the sun. A single teaspoon of neutron star material would weigh roughly the same as a mountain range. Not a mountain, a range. Every grain of it is gravity compressed into something almost beyond analogy. And yet these objects spin. Some of them spin hundreds of times per second, hurling beams of radiation across space with a regularity so precise that when astronomers first detected them in 1967, they briefly, seriously considered the possibility that they were receiving signals from an intelligent civilization. They named the signal LGM-1, Little Green Men. It was, of course, nature, but the instinct was understandable, because the universe, at its most extreme, sounds designed. It sounds deliberate. It sounds, at certain frequencies, almost like a voice. Voices need a center to speak from, or so we instinctively feel. When something calls, we turn toward it. But the universe has no center to turn toward. This is not a poetic statement. It is a geometric one. Space itself is expanding, and it expands everywhere at once, from every point simultaneously. If you were standing in a galaxy a billion light-years from here, you would see all other galaxies moving away from you, just as we see them moving away from us. You would feel, just as we do, like the center of everything, and you would be just as right and just as wrong. There is no address for the middle of the universe. There is no point you could travel to and plant a flag. The cosmos does not have an inside and an outside in the way a room does. It is more like the surface of a balloon being inflated every point, moving away from every other point, and none of them the center. This is one of those truths that the mind accepts before the imagination does. You can say it clearly, and then, quietly, you can sit with how strange it is. Strange, too, is what travels with you through that centerless space, because you are not only made of ancient stellar material, you are also, in a very real sense, on a voyage. The Voyager 1 spacecraft was launched in 1977, before many of the people listening to this were born. It has been traveling ever since, through the solar system, past the planets, through the heliosphere where the sun's influence finally fades, and out into interstellar space. It is the most distant human-made object that has ever existed, and it is still out there, right now, tonight, as you lie here, still moving, still sending back a faint radio signal that takes more than 20 hours to reach Earth, even traveling at the speed of light. A small golden record is attached to it, carrying sounds and images from Earth, a kind of greeting pressed into metal, drifting through the dark. Somewhere beyond the edge of everything familiar, a piece of humanity is traveling quietly through the void. It will not reach another star system for 70,000 years, but it is on its way through a silence unlike any silence you have ever experienced. Because space is not merely quiet in the way a library is quiet, or a field at dawn. Sound requires a medium particles close enough to pass a vibration from one to the next. And in the vast stretches between stars, there are so few particles that sound simply cannot happen. A supernova could detonate a short distance away, a cataclysm releasing more energy than the sun will emit across its entire life, and you would feel nothing if you were standing in open space. No rumble, no pressure wave, no sound at all. The explosion would unfold in total, absolute silence. This is the nature of the cosmos. Immense events, played out in a quiet so deep it has no earthly comparison. The universe is not a noisy place. It is, by almost any measure, the most profoundly silent place that exists. And there is something in that. Something that feels less lonely the longer you sit with it, and more like rest. Rest and something else, a kind of beauty that does not need to be loud to be real. Saturn carries it in its rings. From a distance, they look solid, a flat, gleaming disk wrapped around the planet like a slow halo. But move closer, and they dissolve into something else entirely. Billions of individual pieces of ice, ranging from tiny grains to chunks the size of houses, all orbiting Saturn in a loose, glittering river. The rings are not ancient. On cosmic timescales, they may be relatively young, perhaps only a few 100 million years old, a recent addition to Saturn's long life. And they are not permanent. They are slowly raining down onto Saturn, particles spiraling inward, the rings thinning over geological time. What you see when you look at Saturn is not what Saturn always looked like, and not what it always will. You are catching it at a particular moment in a much longer story, a moment when it happens to be wearing this extraordinary, temporary crown of ice. Timing, in the universe, matters quietly, and at a scale the mind can only approach sideways, because when astronomers turned the Hubble Space Telescope toward a patch of sky no larger than a grain of sand held at arm's length, a patch that appeared, to every instrument, to be empty, they found 10,000 galaxies, each one containing hundreds of billions of stars, each star potentially orbited by worlds. In a speck of apparent nothingness, the universe had hidden an ocean. And what that means, what it really, slowly means, is that emptiness, in the cosmos, is almost never what it appears to be. The dark between things is not absence. It is depth. It is distance. It is the universe doing something we cannot yet see, in a place we have not yet learned to look. Every apparent void, every quiet stretch of black between the familiar points of light, is only empty from where you are standing. From somewhere else, you might be the dark, and someone somewhere might be looking right at you. Looking right at you, though, you would never know it are more stars than the mind can honestly hold. Numbers, at this scale, stop working the way numbers usually work. So set the number aside entirely and try this instead. Every beach you have ever walked, every shoreline you have ever seen in a photograph, every desert and riverbed and playground on this entire planet, gather all of that sand into one vast pile. And then know that the stars in the observable universe outnumber even that. Not by a little, by a margin so large that the sand comparison itself begins to seem almost quaint. And yet each of those stars, the universe is not sparing with its creations. It makes them in quantities that outlast every metaphor we reach for. And still, knowing this, holding this gently, without gripping it, the night sky above you contains not chaos but a kind of order, a web, a pattern, Stars arranged not randomly, but along the slow logic of gravity, pulled into galaxies, galaxies pulled into clusters, clusters into something even larger. The abundance is not noise. It is structure, quietly repeating itself at every scale, all the way up, and all the way back, because some of what you see when you look up is not there anymore. The light from a distant star takes so long to cross the universe that by the time it reaches your eye, the star that sent it may have already ended, collapsed, exploded, cooled into darkness. You are receiving a message from something that no longer exists in the form it had when the message was sent. This is not a melancholy fact, though it can feel like one at first. Think of it instead as a kind of generosity. The star spent its light, sent it outward in every direction, and some small fraction of that ancient generosity is still arriving, still crossing the dark, still completing its journey into the eye of someone lying quietly on a planet that didn't exist when the light left. The star is gone, the light remains, and in the remaining light, something of the star persists not metaphorically, but physically. A photon that left a dying sun 1,000,000 years ago is landing on your retina tonight. You are the end of a very long story you had no idea you were part of. Part of a story that includes the moon, familiar, reliable, hanging in the same sky it has always occupied. And yet, the moon is leaving. Slowly, gently, without drama, it drifts a little further from Earth each year. The distance is small, roughly the thickness of a fingernail, but it is consistent, measurable, real. 4 billion years ago, the moon was much closer. The tides it raised on Earth were enormous, wild things. Days were shorter then. The whole relationship between Earth and its satellite was more intense, more immediate. Over vast stretches of time, the moon has been pulling away, and in pulling away, it has been slowing Earth's rotation, lengthening our days, gently reshaping the conditions that life evolved within. The moon's slow departure has, in some sense, made us possible, and it continues now, tonight, while you sleep, drifting, incrementally, into a slightly lonelier orbit, carrying with it the gravity of everything the Earth and Moon have shared across geological time. Distance, sometimes, is not loss. Sometimes, it is the shape that patience takes. Patience is perhaps the quality most required to understand a black hole, because almost everything people believe about them is slightly wrong. They do not roar. They do not pull everything greedily toward themselves. A black hole, the mass of our sun, would hold Earth in exactly the same orbit that the sun holds it in now. The difference is only what happens when something gets too close past the event horizon, that quiet boundary from which nothing returns. But nothing is being sucked. Nothing is being grabbed. Gravity simply is what it is, and near a black hole, what it is becomes very strong very quietly. Imagine a valley so deep that the path down it curves back on itself, not a trap that reaches out and seizes you, but a geometry you fall into if you wander too close. Black holes are not hungry. They are not waiting. They are simply regions of space where the rules curve more steeply than anywhere else. They have a stillness to them, in concept, that once you sit with it long enough, begins to feel almost peaceful. A place where questions reach their edges, where physics leans into itself and grows quiet. Quietly different, that is how time moves across the universe. Not at a single rate, not ticking the same way everywhere, but shifting with gravity and speed in ways that Einstein described mathematically before anyone could test them. On Venus, a day lasts longer than a year. The planet rotates so slowly on its axis that it completes a full orbit around the sun before it completes a single turn. You would wait for a sunrise longer than the time it takes the planet to travel all the way around its star. And Venus rotates backwards, relative to most other planets, so when the sun finally does rise, it rises in the west. A world where time and direction both refuse to behave as expected, drifting through an orbit in its own unhurried way, indifferent to the schedules we would impose on it. The universe is full of worlds like this. Worlds that keep their own time, that turn at their own pace, that experience day and night in ways no human has ever felt or likely ever will. Time, out there, is not a fixed river. It is something more like weather. Weather that we have glimpsed, if only faintly, in the oldest light we can detect. The cosmic microwave background radiation fills every corner of space right now, in this room, passing through the walls, through the air, through you, as it has been doing since it was released nearly 14 billion years ago, when the universe was about 380,000 years old. It cooled just enough for light to finally travel freely, no longer trapped, no longer bouncing endlessly between charged particles, but released, pouring outward in every direction. That light is still traveling. It has been traveling longer than the Earth has existed. It is the universe's oldest passenger, and it is everywhere simultaneously, a faint microwave glow that permeates all of space with a temperature just a few degrees above absolute zero. Instruments can detect it. Maps have been made of its tiny variations, ripples of slightly warmer and cooler regions that became, over billions of years, the galaxies and clusters and filaments we live among now. You are surrounded, always, by the echo of the beginning. It has never stopped arriving into a universe shaped by things we cannot see. Dark matter does not glow. It does not absorb light. It does not interact with the electromagnetic force in any way that our instruments can directly catch. And yet it makes up roughly 85% of all the matter in the universe. We know it is there because of what the visible matter does, the way galaxies spin too fast at their edges to be held together by their visible mass alone, the way light bends around regions of space that appear empty, the way the cosmic web has exactly the structure that models predict when dark matter is included. Something is there, something vast, ancient, and patient, woven through the fabric of everything, holding galaxies together the way an invisible hand might cup water, without the water knowing it was being held. Scientists are still searching for what it is. Dozens of experiments, buried deep underground to shield them from interference, are listening right now for a dark matter particle to brush against a detector. So far, the silence continues, but the search is patient. And patience, in physics, as in sleep, is often how the best things are finally found. Found not just in what we cannot see, but in how what we can see is arranged. Zoom far enough out from any galaxy, any cluster, any supercluster, and the universe reveals a pattern: vast filaments of matter stretching between dense nodes, with enormous empty voids between them. It looks, with an uncanny precision that has struck every astronomer who has encountered it, like a web, like the threads of silk a spider draws between branches on a dewy morning. And here is the detail that tends to settle quietly into people. That same pattern, the branching, the clustering, the nodes connected by delicate threads, appears in the neural networks of the human brain, not as metaphor, as measurable structural similarity. The network by which the universe organizes its galaxies, and the network by which your brain organizes its thoughts, share a geometry. No one fully understands why. It may be that certain mathematical principles of connection and flow produce similar structures regardless of scale, or it may be something we do not yet have language for. Either way, the universe outside and the universe inside you are, at least in their architecture, quietly rhyming. Rhyming in ways that extend even to the small, cold worlds at the edge of our solar system. Pluto reclassified diminished in popular imagination, visited only once by a spacecraft that took 9 years to arrive, turned out to be extraordinary. When the New Horizons probe finally swept past it in 2015, the images it sent back showed a vast plain of nitrogen ice in the shape of a heart. Not approximately, not vaguely. A clear, unmistakable heart shape, pale and smooth against the darker surrounding terrain, visible from space. Scientists named it Tumor Regio, after the man who discovered Pluto. But the shape remains a heart, at the edge of the solar system, on a small, cold world that spent decades being overlooked. The universe did not put it there for us. It formed through geological processes we are still working to understand. And yet there it sits, a detail so unexpected, so quietly tender, that it is hard not to feel that the solar system, even in its furthest, coldest reaches, holds something worth finding. Finding, sometimes, means turning inward rather than out, because the space inside you is almost as vertiginous as the space between galaxies. Every atom in your body is almost entirely empty. The nucleus at the center of each atom is so small relative to the atom's total size that if you scaled a hydrogen atom up to the size of a cathedral, its nucleus would be no larger than a grain of salt on the floor. Everything else, everything between that grain of salt and the cathedral walls, is empty space, threaded only by fields and forces and the strange, probabilistic blur of electrons. Which means that you, lying here right now, are mostly emptiness. The solidity you feel, the weight of your body against the mattress, the warmth of the blanket, is not the atoms themselves pressing against each other, but the electromagnetic forces between them, repelling and attracting, creating the sensation of substance from something that is, in the deepest physical sense, almost entirely void. You are not as solid as you feel. You are something more like a pattern, a temporary, intricate, beautiful arrangement of almost nothing, holding itself together in the dark, while all around it, through it, past it, beneath any threshold of feeling, the universe is trembling, not metaphorically, physically. When two black holes spiral toward each other across billions of light years and finally merge, they release a disturbance in the fabric of space-time itself, a ripple that travels outward in every direction at the speed of light, passing through everything it encounters, compressing and stretching space by an amount smaller than a proton's width. These are gravitational waves, and in 2015, instruments sensitive enough to detect that almost incomprehensible tremor finally felt one arrive. The universe had been sending these signals for billions of years. We simply had not yet built ears delicate enough to hear them. And now that we have, we are listening to a layer of the cosmos that was always there, a deep, structural hum beneath everything visible, written not in light, but in the geometry of space itself. Right now, as you rest, waves from ancient collisions are passing through this room, through your body, through the earth, a vibration so subtle it registers nowhere in your nervous system, and yet it is real, and it is constant, and it connects you to events of unimaginable scale without asking anything of you at all. At all hours, without pause, the sun is doing something that numbers cannot quite carry. Every second, deep in its core where pressure and temperature reach conditions found nowhere else in the solar system, hydrogen atoms are fused into helium, and in that fusion, a small amount of mass vanishes entirely, converted into energy, according to a relationship so elegant it fits on a single line. 4 million tons of the sun disappear this way every second, not burned, not spent, transformed into the light that crosses space, arrives at Earth, warms the soil, drives the weather, feeds the plants, and ultimately sustains every living thing on this planet. The Sun is not consuming itself carelessly. It has been doing this for nearly 5 billion years and has enough hydrogen remaining to continue for approximately 5 billion more. It is the most patient and generous engine imaginable, converting itself, slowly, into the conditions that make your life possible without ever asking to be noticed. And tonight, while you sleep, it continues. On the other side of the planet, quietly fusing, quietly giving, as it has always done differently on worlds we are only beginning to understand. Europa is one of Jupiter's moons, small, ice-covered, easy to overlook in a solar system full of spectacle. But beneath that shell of ice, which may be tens of kilometers thick, lies a liquid ocean, a body of salt water kept warm, not by a sun, but by the gravitational squeezing of Jupiter's enormous pull, flexing the moon like a slow, gentle hand, generating heat from the inside out. This ocean is estimated to contain more water than all of Earth's oceans combined. It has been liquid, possibly, for billions of years. It sits in darkness, under pressure, in conditions that on Earth we have learned to associate with life, because life on Earth exists in almost exactly those conditions, in the deep ocean trenches where sunlight never reaches, and the pressure would crush an unprotected human instantly. We have not been to Europa's ocean. We have not sampled it or seen it directly, but the mathematics of it, and the biology of what we know, make it one of the quietest and most profound questions in science. What is down there, in the dark, under all that ice, in an ocean that has been waiting longer than complex life has existed on Earth? Earth, with its single sun, sometimes feels like the standard, the template against which other worlds are measured. But scattered through the galaxy are star systems where two suns share a gravitational bond, orbiting each other in a slow, endless waltz. In some of these binary systems, planets exist worlds that experience double sunrises, double shadows, days when both suns are above the horizon and the sky holds two sources of light at once, and nights that come only when both suns have set together. Some binary stars orbit so closely that they share an atmosphere, a single shimmering envelope of gas wrapped around two distinct stellar bodies, neither fully separate, neither fully merged. They exist in a state of intimate proximity that has no human equivalent, each one altering the other's light and gravity and eventual fate. When one of a close binary pair dies, swells into a red giant, sheds its outer layers, the other is there to receive what is given, to be changed by the ending of its companion. Even stars, it seems, do not always travel through time alone, and yet connected the way our own galaxy is connected to things far larger than itself. The Milky Way belongs to a structure called the Laniakea supercluster, a name drawn from Hawaiian meaning immeasurable heaven. It contains the mass of 100 million billion suns, spread across 500 million light-years. And even Laniakea is not the end of it. It sits within a larger cosmic neighborhood, pulled gently toward a gravitational anomaly so massive it has its own name, the Great Attractor. We cannot see it directly. It sits behind the densest part of our own galaxy, hidden behind clouds of dust and star-forming regions that block our view in visible light. We know it is there because of how everything around it moves: galaxies, clusters, our own Milky Way, all drifting in the same direction, drawn by something immense and only partially mapped. Scientists have identified part of it as a supercluster called the Shapley concentration. But whether that accounts for all of the pull is still uncertain. The universe, even in its largest structures, keeps some of its architecture partially hidden. There is always more to find, just beyond the edge of what we can currently see and smell, though the second sense seems to belong nowhere near a conversation about space. And yet, within the vast molecular clouds that drift between stars, the dark, cold nebulae, where new stars are slowly being born, astronomers have detected complex organic molecules. Ethyl formate, in particular, is one of them. It is the molecule responsible for the smell of raspberries. It is also found in rum. These molecules drift in clouds spanning light years, assembled not in a laboratory, but by the slow chemistry of cold gas and cosmic radiation over millions of years. When you imagine a nebula, that soft, luminous smear of color in a telescope photograph, you might now add to the image something unexpected, a faint sweetness. If you could somehow stand inside it and breathe. You cannot, of course. The gas is far too thin, and space offers no air to carry a scent. But the molecule is there. The chemistry is real. And something about knowing that the universe, in its cold and ancient dark, has been quietly assembling the smell of something warm and familiar. That detail does not feel like data. It feels like company. Company that extends further than it sometimes seems. The cosmic web, that vast filamentary structure connecting galaxy clusters across the observable universe, has been measured, modeled, and mapped with increasing precision over the past few decades. And when neuroscientists placed those maps beside detailed images of neural networks in the human brain, the resemblance was not approximate. The branching patterns, the density of nodes, the way connections cluster and thin the measurements of similarity between the two networks, fall within ranges that suggest they are not merely visually alike, but structurally comparable. The universe at its largest scale, and the organ through which you are receiving these words, share a geometry. This is not mysticism. It is a mathematical observation about how complex systems organize themselves when governed by similar principles of flow, gravity, and connection. What it means, in the deepest sense, is still open. But there is something worth sitting with here, the idea that the same logic shaping galaxies may also be shaping thought. That the pattern you use to understand the universe may be, in its architecture, a reflection of the universe itself constant, unhurried in the way a neutron star pulses. Some pulsars rotate hundreds of times every second, their beams of radiation sweeping space, with a regularity more precise than almost any clock humans have built. But not all spinning neutron stars are fast. Some are slow and steady, rotating once every few seconds, their pulses arriving at Earth with a metronomic calm that astronomers can set measurements against. These slower pulsars have been observed for decades, their timing so consistent that any deviation, a slight quickening, a glitch in the rhythm, carries information about the star's interior, its crust, the strange physics happening in matter compressed beyond anything achievable in a laboratory. The pulsar does not know it is being listened to. It simply spins, as it has since the explosion that created it, maintaining its rhythm through the cold and the dark, sending its signal outward in every direction without preference or purpose. And somewhere, a radio telescope is listening, collecting the pulses, counting them, finding in their steadiness a kind of anchor proof that even in the most extreme environments the universe creates, regularity is possible. That rhythm persists, even when conditions seem to forbid it, as they did for hundreds of millions of years after the Big Bang. The universe was dark then, not dim, not twilight. Dark in a way that had no exceptions, no flickering, no gradation. Hydrogen gas-filled space, neutral and opaque, and no stars existed yet to push against it. This era, called the Cosmic Dark Ages, lasted somewhere between 100 and 500 million years, an expanse of time with no light in it at all. And then, slowly, in places where the gas was slightly denser than average, gravity began to win. Clouds collapsed, heat built, and eventually, in dozens or hundreds of locations scattered across the young universe, the first stars ignited. They were enormous, far larger than most stars today, burning hotter and faster, and with a ferocity born of their simplicity, made almost entirely of hydrogen and helium, uncontaminated by any heavier element. They lived briefly and died violently. But in their dying, they seeded space with the first carbon, the first oxygen, the first iron, and in doing so, made everything that came after possible. Every star you see tonight is a descendant of that first, nameless light. Light that travels toward us still, in forms we are only beginning to learn to read, because the universe communicates in more than visible light. It speaks in radio waves, in X-rays, in infrared warmth, in the microwave glow of ancient fire. And it speaks in something far more exotic, cosmic rays. These are not rays in the way the word suggests, not beams of light, but particles, protons and atomic nuclei, flung outward from supernova explosions and the violent neighborhoods around black holes, accelerated to speeds approaching the speed of light, and sent careening across the galaxy for thousands or millions of years before striking something. Often they strike Earth's atmosphere, where they collide with atoms and produce cascades of secondary particles that shower down toward the surface. Some of those particles pass through you regularly right now, tonight, as you lie here without you feeling anything at all. They are cosmic messengers, tiny fragments of distant catastrophes, arriving constantly and silently, passing through walls and blankets and the soft tissue of a sleeping body, carrying in their trajectories the fingerprints of the most energetic events in the universe. You are, even now, being quietly visited by the far edges of everything. Everything that reaches you has traveled a path that was never quite straight. Light, which we think of as the most direct thing in the universe, the very definition of a straight line, bends. Not because it is weak or easily deflected, but because the space it travels through is not flat. Massive objects, galaxies, clusters, the dense invisible halos of dark matter surrounding them, warp the fabric of space-time around them, and light follows that, warping the way water follows the contour of a valley. This is gravitational lensing, and it produces effects that range from subtle to spectacular. A distant galaxy, seen through the gravitational field of a closer one, can appear stretched into an arc, or split into multiple images, or brightened beyond what its own light would achieve alone. Astronomers use this effect, deliberately treating the universe's own mass as a magnifying lens, peering through it at things too faint and far to see any other way. The cosmos, in other words, has provided its own telescope, built not from glass and metal but from gravity and geometry, operating across billions of light years, revealing the ancient and the distant to anyone patient enough to look carefully at what appears, at first glance, to be a simple smear of light. Light that arrives in rhythms, from some sources not continuously, but in pulses so regular they first seemed impossible. A pulsar is what remains after a massive star exhausts itself and collapses, a neutron star spinning rapidly, radiating beams of energy from its magnetic poles. As it rotates, those beams sweep space like a lighthouse beam sweeps the sea. And if Earth happens to lie in the path of that sweep, we receive a pulse with every rotation. Some pulsars complete hundreds of rotations per second. The fastest known spins at over 700 times per second a dead star, the size of a city, rotating faster than a kitchen blender, maintaining a timing precision that rivals atomic clocks. When Jocelyn Bell Burnell first detected a pulsar signal in 1967, the regularity was so inhuman that her research team briefly labeled the source LGM1, Little Green Men. The universe, at its most extreme, had produced something that sounded designed. It was not designed, it was physics, the inevitable consequence of angular momentum preserved through collapse. of a star folding itself into something small and fast, and extraordinarily precise. Nature, given enough pressure, meticulous in ways that stretch back to an age before any star existed. For the first 380,000 years after the Big Bang, the universe was a dense, hot plasma photons and charged particles locked together in a constant, brilliant fog, unable to separate, unable to travel freely. Light existed, but it could not move. It was trapped. And then, as the universe expanded and cooled to a temperature where electrons could settle into orbit around nuclei, the fog cleared not gradually, but in a transition that, on cosmic timescales, was nearly instantaneous. Light poured free. It streamed in every direction across a universe that was, for the first time, transparent. That light is the cosmic microwave background, and it has been traveling ever since for nearly 14 billion years, cooling as space expanded, stretching from the brilliant glow of a young universe into the faint microwave whisper we detect today. The universe did not begin in darkness. It began in a light so complete and so pervasive that darkness had not yet been invented. Darkness came later, as space grew and light thinned. What we live in now, this vast, mostly dark cosmos, is the cooled and quiet aftermath of something that was once all brightness. Brightness of a different kind reaches us through mathematics, through the power of an equation written before its answer was confirmed by sight. When astronomers in the mid-19th century noticed that Uranus was drifting from its predicted orbit, they did not assume their equations were wrong. They assumed something else was there. Two mathematicians, John Couch, Adams and Urbain Le Verrier, independently calculated where an unseen planet would need to be in order to produce that drift. They sent their predictions to observatories, and on the night of the 23rd of September 1846, astronomers pointed their telescope at the calculated position and found Neptune within 1 degree of where mathematics said it would be. A planet discovered not by looking, but by thinking. Not by observation first, but by reasoning that trusted the universe to be consistent, to follow rules, to be, in some fundamental sense, knowable. Neptune had always been there. The equations simply revealed it, the way a key reveals a lock that was always in the wall. The wall of the Milky Way, seen from inside, is a soft band of light arching across the night sky. But the galaxy it belongs to is not the simple flat disk it appears to be. The Milky Way is warped. At its outer edges, the disk bends, curving upward on one side, downward on the other, like the brim of a hat, slowly twisted by an unseen hand. Astronomers confirmed this warp with increasing precision in recent years, mapping the positions of thousands of pulsating stars called Cepheid variables, whose distances can be calculated from the way they brighten and dim. The warp is likely caused by the gravitational influence of the Magellanic Clouds, two smaller galaxies orbiting the Milky Way, tugging at its edges as they pass. Our galaxy, which we often picture as something crisp and symmetrical, is in fact gently, slowly distorted by its companions. It has been shaped by relationship, by proximity, by the long gravitational conversation between neighbors conducted across hundreds of thousands of light years, over billions of years, without a word exchanged. Exchanged instead through light, but even light, that most reliable of messengers, can deceive in one particular way. Stars do not twinkle. This is a fact that takes a moment to settle, because the twinkling seems so fundamental to what a star is: the shimmer, the pulse, the living quality of starlight. But that movement is not in the star. It is in the air between you and the star. Earth's atmosphere is a turbulent, layered medium, full of pockets of different temperature and density, constantly shifting. As starlight passes through it, those pockets refract the light slightly differently from one instant to the next, bending it in, rapidly changing directions, producing the shimmer we call twinkling. Planets, being closer, present a disk wide enough that the atmosphere's turbulence averages out across it so planets glow steadily, while stars dance. Every twinkle is a message about our own atmosphere, not about the star. What we think we are seeing in the star is actually a self-portrait of the air through which we are looking. The universe, observed through our own medium, always carries some reflection of ourselves. Ourselves, anchored to a star and a planet, but the universe contains worlds that belong to neither. Rogue planets drift through the galaxy, without any sun to orbit, untethered, dark, traveling through interstellar space on trajectories shaped by long-past gravitational encounters. They may have formed around a star and been ejected, flung outward by the gravitational dynamics of a young planetary system, sorting itself into order. Or they may have condensed directly from interstellar gas, never belonging to any star at all. Some estimates suggest there could be more rogue planets in the Milky Way than there are stars, a vast, invisible population of cold, silent worlds moving through the dark between the light. Most of them will never be found. They emit no light of their own. They warm nothing. They orbit nothing. They travel, in the deepest sense of the word, alone, and yet they are made of the same elements as Earth, shaped by the same physics, products of the same vast processes that made every world we have ever known. Aloneness, in the universe, does not mean otherness. Otherness is harder to hold on to when you consider what temperature the universe keeps. All of space, the vast stretches between galaxies, the corridors between stars, the empty volumes that dwarf every solid thing, maintains a temperature just barely above absolute zero, about 2.7 degrees on the Kelvin scale, the temperature of the cosmic microwave background radiation, which permeates everything. Space is not cold the way a winter morning is cold. It is cold in a more fundamental way. A coldness that reflects the age and expansion of the universe, the thinning of the energy that once made everything blaze. Absolute zero, the point at which all thermal motion would cease, sits only a few degrees below where space currently rests. The universe is, almost everywhere, almost perfectly still in temperature. What we experience on Earth, warmth, seasons, the heat of a body under a blanket, is the exception. A narrow, improbable band of conditions maintained by distance from a star, by an atmosphere, by the thin and extraordinary luck of being exactly here. The warmth you feel right now is not the universe's default. It is a gift, held carefully, at the edge of a great cold. A great cold that Mars, despite being a neighbor, has made stranger still. When the sun sets on Mars, the sky does not fade through orange and red the way it does on Earth. It does the opposite. The Martian sky, which appears pinkish red during the day due to fine dust particles in the thin atmosphere, shifts toward blue as the sun approaches the horizon. The same dust that gives the daytime sky its warm color scatters blue light preferentially in the low-angle sunlight of dusk. So, on Mars, sunsets are blue, a soft, dusty, alien blue, settling over a landscape of red rock and frozen carbon dioxide. No human has ever watched one in person, but rovers have photographed them, and the images carry a stillness that feels almost familiar. A sun going down, a sky changing color, the day ending, and then something shifts in the image, some detail of hue or texture, and you remember that this is another world entirely, that the sun setting there is smaller than the one setting here, that the silence afterward is absolute, that the blue is real, and no one is there to watch it. Watching, waiting, the dark energy that fills the universe does both, in a sense, though it is not a thing that watches or waits in any conscious way. It is something stranger than that, a property of space itself, perhaps, an energy inherent to the vacuum that does not dilute as the universe expands, but remains constant or possibly grows. In the 1990s, two teams of astronomers studying distant supernova expected to find that the universe's expansion was slowing down, pulled back by gravity as everything pulled on everything else. Instead, they found the opposite. The expansion was accelerating. Galaxies were flying apart faster than they had been before. Something was pushing not from a source, not from a location, but from everywhere simultaneously, woven into the fabric of space. Dark energy. It makes up roughly 70% of everything in the universe, and we do not know what it is. We have named it. We have measured its effects with increasing precision. But its nature, its origin, whether it will remain constant or eventually change, these questions remain open, patient, and vast. Sitting at the center of modern cosmology like a quiet room, whose door we have not yet found a way to open. Open, and ancient the photon traveling toward you from the oldest observable stars has been in motion for nearly as long as the universe has existed. It left its source before the Earth was formed, before the Sun was born, before the Milky Way had settled into the shape it now holds. It crossed distances that have themselves been stretched by cosmic expansion, so that the space it has traversed is far wider now than it was when the journey began. And then, after all of that, after billions of years of uninterrupted travel through the cold and the dark, it arrives. It enters Earth's atmosphere. It passes through your window, or the wall, or the roof above you. And if your eyes happen to be open and aimed in precisely the right direction, at precisely the right moment, it ends its journey on the retina at the back of your eye. One photon, one arrival. The end of a crossing so long that no human unit of time can carry it comfortably. And the eye that receives it, that small, warm, living instrument, does not know, cannot know, simply receives the light and calls it a star and moves on. The universe delivers its oldest messages to us constantly, and we accept them without ceremony, which is perhaps the only appropriate response to something so vast. Vast forces operate near the strangest stars we know. A magnetar is a type of neutron star with a magnetic field so intense that it would begin to affect the quantum properties of matter at a distance of 1,000 kilometers. If one existed in the approximate neighborhood of the moon, which none do, and which is fortunate for every reason, its magnetic field would be strong enough to erase every magnetic stripe on every card in every wallet on Earth. It would pull the iron from your blood. The field lines around a magnetar are not simply strong versions of the fields around a compass or a refrigerator magnet. They are a different order of phenomenon entirely, operating at intensities that have no earthly comparison, and producing effects that stretch into realms of physics still being worked out on paper. Magnetars are rare, and they are distant, and they are, in all practical senses, no concern of yours. But they exist spinning quietly in the galaxy, their fields threading space for thousands of kilometers in every direction, doing physics in the dark that no instrument on Earth can fully replicate. The universe maintains, at its edges, conditions we can describe, but not experience. And perhaps that is enough. Enough material drifts between the stars to fill a cosmos on its own terms. Interstellar space, the vast stretches between stellar systems, is not empty in the way a vacuum chamber is empty. It holds thin clouds of hydrogen and helium, wisps of molecular gas, microscopic dust grains made of carbon and silicates, and the occasional more complex molecule assembled by cosmic radiation over millions of years. It holds magnetic fields threading invisibly through the dark. It holds the remnants of old supernova, expanding shells of gas still moving outward from explosions that happened before our solar system existed. It holds ancient light in the form of the cosmic microwave background. passing through continuously. And it holds, in certain regions, the dense cold clouds where gravity is beginning to win, where matter is slowly gathering toward the threshold at which a new star will form. Interstellar space is not a gap between things. It is a medium, a slow, thin, complex environment through which everything travels and in which nothing is entirely still. The space between things is itself a thing, quietly busy, carrying more history than any solid object it surrounds. Surrounds you, always, in a motion you cannot feel. The solar system is not stationary within the Milky Way. It orbits the galactic center, a journey of such scale that one complete orbit takes approximately 225 million years, a span of time geologists call a cosmic year. The last time the solar system was in roughly this position in its orbit, the Triassic period was just beginning on Earth, and the first dinosaurs were appearing. In the orbit before that, there were no complex land animals at all. In the one before that, life had not yet left the sea. We are, right now, at a particular point in a voyage that has been underway for the entire history of complex life on Earth, moving at over 500,000 miles per hour. You, and everything you have ever known, swept along in the galaxy's slow rotation. None of this motion registers in your body. There is no wind, no sense of speed, no vibration. Only stillness, the profound, ordinary stillness of a Tuesday evening, or a Thursday night, or whatever night this is, in which the Earth carries you gently around the Sun, and the Sun carries you gently around the galaxy, and the galaxy carries you through something larger still. Still, the first stars burned with an intensity that changed everything around them. They were not like the Sun, not yellow, not moderate, not long-lived. They were immense, some of them hundreds of times the mass of our Sun, burning blue-white at temperatures that dwarfed anything in the modern universe. They had no planets, no metals in their atmospheres, nothing but hydrogen and helium, the raw output of the Big Bang, fused in cores of almost incomprehensible heat. They lived for only a few million years, brief, by stellar standards, and then they died in explosions that seeded the surrounding space with the first carbon, the first oxygen, the first nitrogen ever to exist anywhere. These elements drifted outward, cooled, and eventually became part of the next generation of stars and, in some cases, the first planets. The atoms that make your body possible were not present at the universe's beginning. They were manufactured in the deaths of those first, nameless, violent stars assembled in their cores, released in their endings, and sent on a journey of billions of years that eventually arrived here, in this quiet room, in the form of you. You who breathe comets, in a sense because the water in Earth's oceans, and possibly in your own body, may have arrived here partly aboard comets. These ancient objects, remnants from the solar system's formation, are not simply ice and rock. They are chemical libraries carrying organic molecules, amino acids, and water ice that have been preserved in the cold of the outer solar system for billions of years. When comets fall inward toward the Sun, they shed material tails of gas and dust streaming millions of kilometers behind them, and occasionally they strike planets, delivering their cargo directly. The early Earth was bombarded heavily, and some fraction of the water that now fills the oceans may have come from these impacts. The hydrogen in that water is among the oldest matter in the universe, formed in the first few minutes after the Big Bang. Your body is, in part, made of material that is nearly as old as time itself, delivered here by wandering objects on long elliptical paths over billions of years, without intention, without direction, simply following the geometry of gravity until they arrived at a boundary unlike any other, the event horizon of a black hole, which is not a surface in the way a planet has a surface, not a wall, not a visible edge, but a mathematical threshold. The distance from a black hole's center, at which the escape velocity equals the speed of light. Inside that radius, nothing, no matter, no light, no information can escape. Not because something holds it there, but because the geometry of space-time itself curves back on itself completely. An astronaut falling toward a black hole would not feel the moment of crossing. There is no membrane, no physical barrier. The event horizon would be invisible, unmarked, indistinguishable from the space just outside it. And yet, once crossed, everything changes, not in the astronaut's experience, which would continue normally for a time, but in the structure of possible futures. All futures, from that point, lead inward. The concept is one that the mind approaches slowly, from the outside, like a shoreline that looks firm, until you realize the tide has already come in around you. The universe contains places from which there is no returning, and in a strange way, knowing they exist makes the place where you are feel very specifically and gently like somewhere worth being. Being here, on this particular world, means living inside an atmosphere that does something almost invisible and entirely essential. Starlight does not twinkle, because stars shimmer. We established that already, in another quieter moment. But consider what that atmospheric turbulence means more broadly. We are wrapped in a layer of moving air that distorts, filters, absorbs, and redirects the light coming from the rest of the universe. Every observation made from Earth's surface is made through this veil. Infrared light is absorbed by water vapor. Ultraviolet light is blocked by ozone. Radio waves of certain frequencies bounce off the ionosphere. Only a narrow band of the electromagnetic spectrum reaches the ground unimpeded visible light and some radio waves. Everything else requires a telescope in space. What this means is that the picture of the universe we built across most of human history, everything Galileo saw, everything the great observatories of the 19th century recorded, was assembled from a thin slice of what was actually arriving. We were reading the universe through a keyhole. Space telescopes opened the door, and what was behind it turned out to be stranger and richer and more layered than the keyhole had suggested. Suggested, perhaps, by the long quiet of space itself, a quiet that Neptune, for all its distance, has always maintained. When Voyager 2 flew past Neptune in 1989, it found a planet of deep blue, swept by the fastest winds in the solar system, circled by a moon called Triton, that orbits backward opposite to Neptune's rotation, suggesting it was captured from elsewhere, a wanderer that fell into Neptune's gravity and never left. Triton's surface is covered in nitrogen ice, with geysers that erupt dark plumes into the thin atmosphere, active geology, on a moon so cold that its surface temperature approaches absolute zero, and Triton is slowly spiraling inward. In approximately 3.5 billion years, it will cross the Roche limit, the distance at which Neptune's tidal forces will overcome Triton's own gravity, and the moon will break apart, its material spreading into a ring around the planet. A moon becoming a ring, a companion, becoming an adornment. The solar system is always in the middle of a story, and every object in it is moving toward a different version of itself. Itself moving, always the Milky Way, not as a fixed backdrop, but as a participant in something larger. Andromeda, our nearest large galactic neighbor, is approaching. Not quickly by human standards, the merger is approximately 4.5 billion years away. But the gravitational conversation between the two galaxies has already begun. They are already influencing each other subtly, already beginning the long approach that will end in a collision spanning hundreds of millions of years. The word collision is misleading. Stars are so far apart that when galaxies merge, Individual stars almost never actually strike one another. What happens instead is a vast gravitational reshaping stars flung into new orbits, spiral arms distorted and unwound, gas clouds compressed into bursts of new star formation, the two galactic centers slowly sinking toward each other until they merge into a single elliptical galaxy. Astronomers have already named Milkomeda. Our solar system will likely survive, though in a different location within the new structure. And the night sky, over those hundreds of millions of years, will slowly transform new stars blooming in the sky as the two galaxies breathe into each other. The familiar patterns dissolving into something new, something neither galaxy could have become alone. Alone in the dark between stars, a rogue planet drifts, but even that darkness is not uniform. The universe maintains a temperature everywhere, a faint and pervasive cold that is the stretched remnant of ancient fire. Yet, even this cold has texture. In the large empty spaces between galaxy filaments, the cosmic voids, the temperature of matter, the density of gas, the frequency of passing photons, all differ subtly from the regions where galaxies cluster. Voids are not simply absences, they are environments. Low-density regions where the expansion of the universe proceeds slightly faster, where dark energy's influence is relatively less opposed by the gravitational pull of matter. Galaxies at the edges of voids tend to be younger-looking, bluer, still-forming stars, as though proximity to emptiness keeps something alive in them that the crowded cluster galaxies have slowly lost. The void shapes what surrounds it. Emptiness, in the universe, is not passive. It pushes back gently, consistently, across millions of light years, influencing the motion and nature of everything gathered at its edges. Even nothing in the cosmos participates in a universe that contains, right now, a star in the act of being born. Somewhere in the Milky Way, in one of the cold, dense molecular clouds that drift through the galaxy's spiral arms, a pocket of gas has crossed the threshold. Gravity has won its slow argument with pressure and turbulence. The cloud is collapsing inward, heating as it falls, the center growing denser and warmer by degrees over thousands of years. Eventually, not tonight, not in any human lifetime, but eventually the core will reach the temperature at which hydrogen fusion ignites, and a new star will announce itself. It will blow away the remaining cloud with its first light, and what remains around it may be a disk of gas and dust from which planets form. This is happening right now, in the dark, in silence, unremarked by any observer. The universe does not wait for witnesses. It simply continues its processes, collapsing, igniting, creating with the same patience it has maintained for nearly 14 billion years. Stars are being born tonight. The cosmos is, even now, making more of itself. Itself built from light, bent by gravity, and gravity, it turns out, bends time as well. This is not metaphor, it is measurable. Clocks at higher altitudes run slightly faster than clocks at sea level, because they are fractionally farther from the center of Earth's gravitational field. The difference is small nanoseconds per day, but it is real, and it matters. The GPS satellites orbiting Earth must account for this difference in their calculations, or the navigation errors they produce would accumulate rapidly. Einstein predicted this effect, gravitational time dilation, as a consequence of general relativity, and every precise measurement since has confirmed it. Time, in other words, is not a river flowing at a single rate. It flows at different speeds depending on where you are in a gravitational field. On the surface of a neutron star, where gravity is extreme, time would pass measurably slower than here. Near the event horizon of a black hole, the difference becomes profound. And here, tonight, on the surface of this ordinary planet, time is passing for you at a rate slightly different. from someone on a mountaintop. Gravity holds you, and in holding you, it slows you gently, imperceptibly, continuously. Continuously threaded through the galaxy are magnetic fields that no eye can see and no hand can feel. Yet they shape the behavior of matter at every scale. In the space between stars, magnetic fields align the spinning dust grains that drift through the interstellar medium, influence where molecular clouds collapse, and guide the paths of cosmic rays as they travel through the galaxy. Within star-forming regions, magnetic fields resist collapse, acting as a slow brake on the process of starbirth, determining not just whether a cloud collapses but how quickly and what mass of star emerges. Around pulsars, magnetic fields a trillion times stronger than Earth's produce the radiation beams that sweep space. And in the broader galaxy, a weak but vast magnetic field threads through the spiral arms, its origin and maintenance still not fully understood. We live inside a magnetized galaxy. The space through which we move is not neutral. It is threaded with invisible structure, fields that have direction and strength, and history, accumulated over billions of years of stellar births and deaths, and the slow churning of the galactic disk. The cosmos is not empty between the visible things. It is organized, subtly, in ways we are still learning to read. Read in a language written in ice and cold on Titan, Saturn's largest moon, where rivers run and rain falls and lakes gather at the poles, but where none of it is water. The liquid on Titan is methane natural gas, the same substance that burns in kitchen stoves, existing in liquid form on Titan's surface, because the moon is so cold that methane behaves there the way water behaves here. It evaporates from the surface, forms clouds in the thick nitrogen atmosphere, falls as rain, flows in rivers carved into the landscape over millions of years, and collects in lakes near the poles that the Cassini spacecraft mapped in careful detail. The largest of these lakes, Kraken Mare, is larger than the Caspian Sea. Titan has a complete hydrological cycle, as Earth does, but running on a different chemical entirely. It is the only world besides Earth known to have stable liquid on its surface. What that means for the possibility of life, whether life could exist in liquid methane the way it exists in liquid water, is genuinely unknown. Scientists debate it carefully, with appropriate uncertainty, but the question sits there, patient and open. In a methane lake on a cold orange moon, is something happening? Happening everywhere, at every moment the universe expanding. Not the galaxies moving through space, but space itself stretching. The distance between galaxies increasing not because they are traveling, but because the medium they inhabit is growing. And this expansion is not slowing. In the late 1990s, two independent teams studying distant supernova standard candles, whose intrinsic brightness is well understood, found that the most distant ones were dimmer than expected. They were farther away than the expansion rate should have placed them. The universe was not just expanding, it was expanding faster than it had been before, the rate accelerating over time. Something was pushing space apart with increasing urgency. That something, dark energy, remains the largest single component of the universe's energy budget, accounting for roughly 70% of everything, and its nature is one of the most genuinely open questions in science. Whether it is a fixed property of space, or a field that changes over time, or something stranger still, the honest answer is that no one knows. The universe's dominant ingredient is, at present, a mystery held inside a name given in the relative quiet of the present, but some stars have been burning since the universe itself was young. Population 2 stars, formed in the first billion years of cosmic history from gas that contained almost no elements heavier than hydrogen and helium, are still alive. Some of them are among the oldest objects we can observe, dim, cool red dwarfs that burn so slowly and so efficiently that they can persist for hundreds of billions of years, far longer than the current age of the universe. One star, designated HD 140283, and sometimes called the Methuselah star, was initially estimated to be older than the universe itself, a measurement that briefly unsettled cosmology before refined calculations brought its age into uncomfortable but possible alignment with the universe's timeline. The oldest stars carry in their compositions the record of the early universe: almost no iron, almost no carbon, almost no oxygen, a chemical simplicity that marks them as survivors from before the first supernova had enriched the interstellar medium. They are ancient in a way that makes the word ancient feel inadequate. They have been burning since before the Earth's sun existed, before the Milky Way had its current shape, before most of the universe's stars had yet been born. Born of processes that left a fingerprint on the oldest light because the cosmic microwave background radiation, that faint, pervasive glow, is not quite uniform. It has a polarization. The photons that make up the cosmic microwave background oscillate, and they do not oscillate in random directions. They show patterns, subtle preferred orientations that encode information about conditions at the moment of last scattering, 380,000 years after the Big Bang. Some of these polarization patterns, called B-modes, would, if detected clearly, constitute direct evidence of gravitational waves produced during cosmic inflation, ripples in space-time from the universe's first fraction of a second. Instruments have been searching for these patterns with increasing sensitivity. Some signals have been found. Their interpretation remains carefully debated. The polarization of ancient light is, in this sense, a message from the very beginning, not just from the universe's infancy, but from its first instant, written in the orientation of photons that have been traveling ever since, carrying their signal patiently across all the time there has been here. The water in your body older than you know. The hydrogen atoms in every water molecule, in every cell of your body, were formed in the first 3 minutes after the Big Bang, in a process called Big Bang nucleosynthesis. When the universe was young and hot enough for nuclear fusion to occur everywhere simultaneously, protons and neutrons combined to form the first atomic nuclei, hydrogen, helium, and trace amounts of lithium. Those hydrogen nuclei have existed ever since. They have been inside stars, inside nebulae, inside comets, inside oceans, inside rain, inside other living things, inside rivers, inside clouds, cycling through the universe's matter for nearly 14 billion years before ending up, for this particular moment, inside you. The hydrogen bonding your water molecules together tonight is among the oldest matter in existence. You are not a recent thing, assembled from new materials. You are a temporary arrangement of some of the universe's most ancient ingredients, held together for a brief and particular time, in a form that can wonder about its own origins. Origins written in acoustic waves are details so unlikely it still carries surprise even after explanation. In the early universe, before recombination, matter and radiation were coupled together in a hot plasma that rippled with sound waves, pressure waves, moving through the dense medium at more than half the speed of light. These waves had a characteristic scale, determined by how far sound could travel in the time between the Big Bang and recombination. When recombination occurred and the plasma froze into neutral gas, those sound waves were imprinted on the distribution of matter, and that imprint has persisted ever since, stretched by the expansion of the universe, visible today in the subtle clustering of galaxies at a preferred separation of roughly 500 million light-years. Astronomers call this baryon acoustic oscillation, a pattern in the large-scale structure of the universe. That is, in a precise and literal sense, the fossilized echo of sound. The universe rang, once, in its infancy, and the arrangement of galaxies we observe today is, in part, the shape that ringing left behind a melody written in matter, stretched across the sky, still readable if you know how to look. Look, and you find that some of the universe's most important structures are also its most counterintuitive. A white dwarf is what remains when a star like our Sun exhausts its hydrogen, swells into a red giant, and then sheds its outer layers, leaving behind the compressed core no longer fusing, no longer generating energy, simply cooling, slowly, over timescales that stretch beyond anything biology can compass. A white dwarf loses heat so gradually that even the oldest ones in the universe, those that formed in the galaxy's earliest stellar generations, have not yet cooled to darkness. They are still warm, still faintly luminous, and the universe is not old enough to have produced a cold, dead white dwarf, yet not a single one, anywhere. In 100 billion years, the first black dwarfs will begin to appear, dark, cold stellar remnants, the final state of stars, like our Sun. But right now, in the current universe, they do not exist. Every white dwarf that has ever formed is still warm, still radiating, still completing a cooling process that will outlast every star currently burning in the sky. The universe is, by this measure, still very young. The longest stories have not yet reached their endings. Endings that dark energy may write, across a timescale almost beyond imagining. As the universe continues to accelerate its expansion, galaxies beyond a certain distance are already receding from us faster than light, not because they are moving through space faster than light, but because the space between us and them is growing so rapidly that light from them will never reach us. Over billions of years, more and more galaxies will cross this horizon, their light redshifting toward invisibility, their signals thinning to nothing. The local group, the Milky Way, Andromeda, and a few dozen smaller galaxies bound to us gravitationally will remain accessible, merged eventually into a single structure. But beyond it, the universe will grow increasingly dark and empty, not because things are disappearing, but because distance is becoming permanent. Civilizations in the far future, if any exist, may look out at a night sky containing only their own galaxy. The evidence for the universe's true scale, the billions of other galaxies we can see tonight, will be gone, moved beyond reach. We live, right now, in the best era for observing the universe that will ever exist. The view is better tonight than it will ever be again. Again and again the cosmos offers water not just here, but everywhere. Comets carry it. Asteroids carry it. The atmosphere of certain exoplanets shows its signature. In the vast molecular clouds between stars, water ice coats the surfaces of dust grains, assembling in the cold, dark through simple chemistry that requires nothing more than hydrogen, oxygen, and time. Water has been detected in the disk of gas surrounding young stars, in the plumes erupting from Saturn's moon Enceladus, in the permanently shadowed craters of the Moon and Mercury, where sunlight never reaches and ancient ice persists undisturbed for billions of years. Water is not a special product of Earth. It is a common output of the universe's chemistry, assembled wherever the right elements meet at the right temperatures, preserved wherever cold and shadow cooperate. That the molecule most essential to every living thing we have ever found is also one of the most common molecules in the universe, is either a remarkable coincidence or a clue about the nature of life itself, a suggestion that life did not arise in spite of the universe's conditions, but because of them, that the universe, in some sense, was always going to make something like us, looking outward through instruments of extraordinary delicacy. The James Webb Space Telescope was designed to observe the infrared universe with a precision that requires its primary mirror to be cooled to within a few degrees of absolute zero and its detectors to be shielded from the sun, the Earth, and even the Moon by a sun shield the size of a tennis court. Its sensitivity is such that it could, in principle, detect the thermal signature of a bumblebee at the distance of the Moon. Not the bee itself, not its color or shape, but the faint warmth of its body radiating in the infrared. This is not a metaphor for capability. It is a calibration, a way of translating what the instrument can do into terms the body can feel. And what it does with that sensitivity is look back in time, observing the first galaxies, the atmospheres of distant worlds, the composition of nebulae, the light that left its sources when the universe was a fraction of its current age. Webb sees in wavelengths the human eye cannot detect, in a universe that keeps most of its information outside the narrow band our biology evolved to perceive. Every image it returns is a reminder that what we see unaided is the smallest possible slice of what is there. There, in the outer reaches of our own solar system, diamonds fall. On Uranus and Neptune, the ice giants, cold and remote, visited by spacecraft. Only once the conditions deep in the atmosphere create pressures and temperatures that compress carbon into crystalline structures and allow them to precipitate downward through the layers of dense fluid. Diamond rain. The idea was proposed theoretically and has been supported by laboratory experiments that recreate the relevant pressures, watching as hydrocarbon compounds crystallize under the right conditions. The diamonds that form would not be gem-sized, at least not near the surface layers, but deeper still, where pressure becomes extreme. Some models suggest they might accumulate, settling toward the planetary core, building over geological time. What exactly happens to them there, whether they dissolve, accumulate, or become part of some exotic interior structure, is still uncertain. But the principle holds. In the cold outer solar system, on planets that look from Earth like featureless blue spheres, something is falling through the dark interior that on Earth we associate with rarity and value. The universe is far less careful with its treasures than we are. We are careful, on the other hand, about what we can observe, and the observable universe is not the whole universe. It is only the region from which light has had time to reach us since the Big Bang. Beyond our cosmic horizon, space continues, possibly forever, possibly containing more galaxies, more structures, more complexity, but their light has not arrived, and may never arrive, because the universe's expansion means some distances are growing faster than light can cross them. The observable universe is, in this sense, a bubble, not a boundary in space, but a boundary in time and light. We sit at its center not because we are special, but because the horizon is defined by our vantage point, and any observer anywhere would see themselves at the center of their own observable universe. What lies beyond our horizon is not nothing. It is simply unreachable with current instruments, current physics, current light. Whether the universe beyond is similar to what we see, or radically different, whether our cosmic bubble is representative or exceptional, is a question that observation, by its nature, may never be able to answer. Some questions are defined by the limits of the place you are asking them from. From the sun, every second, more energy pours outward than humanity has used in all of recorded civilization combined. This is not an exaggeration for effect. The sun radiates approximately 3.8 times 10 to the power of 26 watts, a number so large that multiplying it by any ordinary human activity produces something incomprehensible. In the time it takes you to draw a single breath, the sun has released more energy than every power plant ever built on Earth has produced across all of human history. And the sun is a fairly ordinary star, not large, not particularly luminous by galactic standards, sitting in the middle of the main sequence, burning steadily and without drama. The extravagant stars, the blue supergiants and luminous blue variables, outshine it by factors of millions. Energy, in the universe, is not scarce. It is produced in quantities that leave every human conception of abundance looking modest. What we call power, on Earth, is a thread, a single thread, in a tapestry of energy production that spans the galaxy and has been ongoing for billions of years. We are not the scale at which the universe measures its output. We are much smaller, and somehow that is a relief. Relieving too is the shape of where we are. The universe's geometry, its large-scale curvature, has been measured with increasing precision through observations of the cosmic microwave background and the distribution of galaxies. And what those measurements show is that the universe is, on the largest scales, flat. Not flat like a table flat in the geometric sense, meaning that the angles of a triangle drawn across cosmic distances add up to exactly 180 degrees, that parallel lines remain parallel, that the universe does not curve back on itself into a closed sphere or open outward into a hyperbolic saddle. This flatness implies a precise balance between the universe's total energy density and its expansion rate, a balance so exact that it is itself a puzzle, one of the things that inflationary cosmology was partly designed to explain. A flat universe is, in the current models, one that expands forever, not collapsing, not tearing apart, but continuing, cooling, thinning, persisting. Whatever the universe's long future holds, it is not a finite end. It is an indefinite continuation into a cold and quiet expansion that simply goes on, without boundary, without destination, into something that has no name yet stars are still being born in it, and the process of their birth begins with grains of dust so small they are invisible to any unaided sense. Cosmic dust particles, micron-scale grains of carbon, silicate minerals, and ice drift through the interstellar medium, coating the inner surfaces of molecular clouds, absorbing and re-radiating energy, helping the clouds cool. And cooling is essential. Without cooling, a molecular cloud retains enough thermal pressure to resist the collapse of gravity. Dust allows the cloud to shed heat, slowly lowering its temperature until gravity can begin to draw it inward. Dust also provides surfaces on which simple molecules can meet and bond, surfaces where hydrogen atoms land, find each other, and leave as hydrogen molecules, where more complex chemistry slowly assembles in the cold. These tiny grains are the universe's catalyst, small beyond imagining, present in vast quantities, quietly enabling the processes that make stars and planets and, eventually, the conditions in which life can arise. The cosmos builds its grandest structures from its smallest pieces, and the smallest pieces do their work in patience and in cold, in the dark between things, without any awareness of what they are helping to become. Become what we are assembled, temporarily, from matter that has cycled through the universe many times. The left hand and the right hand, resting on the blanket above you tonight, may have been born in different stars. Not metaphorically, the atoms composing different parts of your body arrived here through different pathways, from different stellar sources, having traveled different routes through the interstellar medium, before being incorporated into the cloud that became the solar system. There is no reason your left hand and your right hand should share an origin. The iron in your blood came from supernova. The calcium in your bones may have been produced in the final stages of a massive star's life. The carbon that forms the backbone of every organic molecule in your body was assembled inside a red giant. These elements did not know they were on their way to becoming a person. They were simply following the physics, moving through space. gathering in clouds, forming stars, being expelled in stellar winds and explosions, drifting again and gathering again. You are not one thing that was made. You are many things that found each other across vast distances and vast time, and arrange themselves, for this moment, into something that can lie quietly in the dark and wonder where it came from. Came from a beginning that was not a beginning in any ordinary sense. The Big Bang was not an explosion that happened somewhere. It was not a fireball expanding into existing space, the way a bomb expands into existing air. Space itself did not exist before it. Time itself did not exist before it. The question of what came before the Big Bang is not a question physics can currently answer, not because we haven't looked hard enough, but because the concept of before requires time, and time began with the universe. Whatever the Big Bang was, it was not an event inside a larger context. It was the context itself, coming into being. Space expanding from everywhere at once, time beginning to pass, energy and matter emerging from conditions so extreme that our equations approach their limits and begin to lose their footing. Cosmologists work carefully at this edge, not claiming certainty where there is none, not filling the silence with confident answers, but tracing the equations as far as they go and noting, honestly, where they stop. The universe's beginning is not a mystery for lack of trying. It is a mystery that lives at the very edge of what questions can be asked. And sitting with the genuine, unresolved openness of it, has a quality that is less like frustration and more like standing at the shore of something immeasurably wide enough to hold stars that share more than a neighborhood. In close binary systems where two stars orbit near each other, the larger star, as it ages and swells, can overflow its own gravitational boundary, spilling material across the space between them onto its companion. The companion receives this gift whether it wants it or not, its mass increasing, its behavior changing, sometimes its fate altered entirely. If the receiving star is a white dwarf, the accumulated material can eventually reach a threshold, a critical mass that triggers a thermonuclear explosion across the entire surface of the star simultaneously. This is a Type Ia supernova, a detonation so consistent in its brightness that astronomers use it as a standard candle to measure distances across the universe. The discovery that the universe's expansion is accelerating the finding that revealed dark energy rested on these explosions, on the light of dying stars in binary systems, billions of light-years away. The intimacy of two stars sharing material across a narrow bridge of gravity became, in the hands of careful astronomers, the instrument by which the universe's largest secret was uncovered. Uncovered slowly, the way gravitational time dilation reveals itself not in drama, but in the accumulation of tiny, consistent differences. On a mountaintop, time passes fractionally faster than at sea level. In the cabin of a commercial aircraft, clocks gain nanoseconds relative to clocks on the ground over the course of a long flight. These are not theoretical curiosities. They are real enough that GPS satellites, orbiting at altitude, moving at speed, sitting in a weaker gravitational field, must correct for both special and general relativistic effects in their timing, or navigation errors would grow to roughly 10 kilometers per day. Relativity is not an abstraction that lives in equations. It is baked into the technology of everyday life, quietly maintaining the precision on which modern navigation depends. Every time a phone locates itself on a map, it is, in a small but real sense, applying Einstein's insight that space and time are not fixed, that they flex, that they respond to mass and motion, that the universe is not a rigid stage on which events play out, but a dynamic medium that participates in everything happening within it. The universe is not the background, it is part of the story. The story holds things we cannot see and forces we cannot touch. And yet the sky between the stars is not neutral. It is magnetized, weakly but pervasively. The field lines threading through the interstellar medium in patterns shaped by the motion of gas, the rotation of the galaxy, the memory of ancient supernova. These fields are not strong by any earthly standard. They would not deflect a compass needle, but they extend across thousands of light years, and in that extension they do something remarkable. They guide the paths of cosmic rays, bending their trajectories as they travel through the galaxy, spreading them more evenly than they would otherwise be. They help align the dust grains that drift through the interstellar medium, tiny, elongated grains that rotate with their long axes perpendicular to the field, like weather vanes, settling in a gentle and consistent breeze. This alignment affects how light passes through these regions, imprinting a polarization that astronomers can measure. The invisible magnetic architecture of the galaxy is written subtly in the orientation of light that passes through it. The galaxy tells its own structure to anyone who knows how to ask. Ask the right question of the right wavelength of light, and a neutron star will sometimes answer with something that strains description. A magnetar, the most intensely magnetized object known to exist, occasionally releases a starquake, a sudden fracture or adjustment in its crystalline neutron-rich crust, releasing energy in a fraction of a second that, for that instant, outshines the entire galaxy. On 27 December 2004, a magnetar called SGR 1000, 806-20, released a flare so powerful that it measurably affected Earth's ionosphere from 50,000 light-years away, compressing it briefly, changing the behavior of radio waves bouncing off it, detectable by instruments around the world. The event lasted about 0.2 of a second. In that 0.2 of a second, it released more energy than the sun emits in 250,000 years. And then it was over. The magnetar settled. The ionosphere recovered. The instruments recorded what had happened. And the universe continued, as it always does, without particular ceremony, having briefly, casually, produced something that no human technology could approach from a distance so large that what arrived here was only the faintest shadow of the event itself. Itself changing, always, because quantum mechanics insists that even empty space cannot be still. The vacuum is not nothing. At the quantum level, pairs of virtual particles flicker into existence and annihilate each other continuously, borrowing energy from the vacuum for intervals so brief they fall within the uncertainty principle's allowances. This quantum foam seething, flickering, never quite empty, has measurable physical effects. The Casimir effect, demonstrable in a laboratory, arises when two uncharged metal plates are placed extremely close together in a vacuum. The quantum fluctuations between them are constrained, while those outside are not, creating a tiny but real pressure, pushing the plates together. The vacuum pushes. Empty space has energy, and this zero-point energy of the vacuum may be related in ways physicists are still carefully working out to dark energy itself, to the force driving the universe's acceleration. The emptiest places in the universe are not resting. They are busy with something so small and so fast that it sits below every threshold of ordinary experience, maintaining an activity that has been continuous since the beginning of time. Time that has carried, from its earliest moments, a kind of fossil radiation that surrounds you right now, without your feeling it at all. The cosmic neutrino background, the relic neutrinos decoupled from matter within the first second after the Big Bang, fills the universe just as the cosmic microwave background does, but is far harder to detect. Neutrinos interact with matter so rarely that the entire Earth is nearly transparent to them. They pass through you in their trillions every second, without leaving any trace your body could register. And yet they are there. These ancient particles, streaming through space since the universe was 1 second old, older than any atom, older than any nucleus, heavier than hydrogen, older than the light we call the cosmic microwave background. They carry information about that first second in their energies and their distribution. Detecting them directly remains one of the great unsolved challenges of experimental physics, requiring instruments of a sensitivity and scale not yet built. But they are here, the universe's oldest travelers, passing through walls and planets and the soft tissue of sleeping bodies, indifferent to everything, ancient beyond all ordinary comparison, threading through this moment as they have threaded through every moment since nearly the beginning. Beginning with questions is often how the largest discoveries happen, and sometimes the sky itself poses them. The Great Attractor sits in a direction we can barely see behind the densest plane of the Milky Way, in a region of sky so crowded with gas and dust, and stars that optical telescopes find it nearly opaque. In X-ray and radio wavelengths, which penetrate that obscuring material more easily, we can begin to map what lies beyond. The Norma cluster is there, and behind it, the Shapley supercluster, one of the most massive concentrations of matter in the observable universe. But whether these structures fully account for the gravitational anomaly drawing our galaxy and its neighbors toward that region, whether we have found the whole of the Great Attractor or only part of it, remains genuinely uncertain. The Milky Way itself blocks our best view of a significant portion of the universe. We live inside a galaxy that obscures part of the cosmos from us, the way a forest obscures the view from within it. The universe contains directions we cannot yet fully see, answers hidden behind our own home, mysteries located not at the edge of observation but directly behind the structure we inhabit. Inhabit as a species that has, in just a few decades, sent its first emissaries beyond the solar system. Voyager 1 crossed into interstellar space in 2012, leaving the heliosphere, the vast bubble of solar wind inflated by our sun, and entering the thin plasma of the interstellar medium for the first time. It now travels through the space between stars, sampling the environment directly, sending back data about particle densities and magnetic field orientations in a region no instrument had ever reached. It carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, music from many cultures, greetings in 55 languages, the sound of rain, of surf, of a mother's first words to a newborn child. The record was assembled in 1977, chosen by a committee that included Carl Sagan, with the understanding that it might travel for billions of years without being found. It was not assembled with confidence. It was assembled with hope, the kind of hope that does not require a likely outcome, only the willingness to send something into the dark and trust that the gesture itself has meaning, regardless of what receives it or when. When you look at the sky on a clear night from a dark place, you can see, with your unaided eye, the Andromeda Galaxy, a faint, soft smear of light in the direction of the constellation of the same name. What you are seeing is the combined light of approximately 1 trillion stars, arriving at your eye after a journey of approximately 2.5 million years. The light left Andromeda before Homo sapiens existed. It traveled through the intergalactic medium, through the outskirts of the Milky Way, through the atmosphere of Earth, and landed on your retina, a retina that evolved for entirely different purposes, in an entirely different context, with no awareness that it would one day find itself receiving ancient light from another galaxy. The fact that this is possible with no instrument at all, no telescope, no detector, no technology beyond the biology you were born with, means that the universe has, in a sense, arranged itself so that a human standing in a field at night can reach out with nothing but their eyes and touch something 2.5 million light years away. That is not nothing. That is, quietly, one of the most extraordinary things there is. Extraordinary, and yet operating by rules so consistent they border on the serene. Quantum mechanics, the physics of the very small permits, something that sounds like it should be impossible. A particle existing in multiple states simultaneously, its properties not fixed until the moment of measurement. An electron is not somewhere specific until something interacts with it. It occupies a probability cloud, a smear of possible locations, each with its own likelihood, and only when observed does it resolve into a single, definite place. This is not a limitation of our instruments. It is not that the electron is somewhere and we simply cannot find it. The electron genuinely does not have a fixed position until the act of measurement forces the question. The universe at its smallest scale is not a collection of tiny billiard balls moving along predictable trajectories. It is something more like a field of tendencies, of likelihoods, of potential that crystallizes only when pressed. And you are made of this. Every atom in your body is governed by these same uncertain rules, its electrons existing in probability clouds, its behavior fundamentally indeterminate at the deepest level. The solidity of the world, the certainty of the blanket, the floor, the walls, emerges from something that is, at its foundation, irreducibly and permanently fuzzy. Certainty, in the universe, is always something that arises. It is never something that was there to begin with. With instruments sensitive beyond what intuition allows, physicists in 2015 detected something that had been predicted a century earlier and never directly observed. When two black holes, one 36 times the mass of the Sun, the other 29, completed their final spiral and merged approximately 1.3 billion light-years away, they released a gravitational wave. That wave traveled outward at the speed of light, passing through everything it encountered, compressing and stretching the fabric of space-time by an amount smaller than 1,000th the diameter of a proton. When it reached Earth, two detectors separated by 3,000 kilometers, their mirrors isolated from every possible vibration by systems of extraordinary complexity, felt it. The signal lasted less than a second. It was a chirp, a rising frequency. The last few orbits of two black holes translated into a sound that, when played through a speaker, resembles something between a whisper and a heartbeat. The universe had been sending these signals for billions of years. We had simply not yet learned to listen. And when we finally did, the first thing we heard was the sound of two black holes becoming one, a billion years before anyone was listening. Listening to a universe that may be only one of many. The theory of eternal inflation, an extension of the inflationary model of the universe's earliest moments, suggests that the rapid expansion that smoothed and flattened our universe may not have ended everywhere, simultaneously. In some regions, inflation may have stopped, forming a bubble of stable space, our universe, while elsewhere inflation continued, eventually producing other bubbles, other universes, each with its own physical constants, its own laws, its own history. This multiverse is not a confirmed reality. It is a mathematical consequence of certain well-supported models, and whether it constitutes a genuine prediction or an untestable extrapolation is debated carefully among cosmologists. No observation can currently reach beyond our cosmic horizon to test it. But the mathematics that produces it is the same mathematics that correctly predicts the fluctuations in the cosmic microwave background, the formation of large-scale structure, and the geometry of our universe. It is a possibility held honestly, neither dismissed nor overclaimed, sitting at the edge of what physics can say, in the quiet space where science and wonder share a border. Border conditions on Pluto are unlike anything in the inner solar system. As the long night of Pluto's year descends, and a Pluto year lasts 248 Earth years, the nitrogen that sits as ice on Tumor Radio, the great heart-shaped plain, sublimates slowly into a thin atmosphere during the warmer months, then freezes back down as temperatures drop. This cycle of nitrogen-breathing atmosphere thickening and thinning with the long, slow seasons shapes the surface in subtle ways, depositing frost in some regions and eroding it in others. The heart shape itself may be maintained partly by this atmospheric cycle, the nitrogen ice accumulating preferentially in a low-lying basin, a world at the edge of the solar system, in temperatures 230 degrees below zero on the Celsius scale, is still doing geology, still cycling its materials, still changing, slowly, in response to its relationship with a sun so distant, it appears as little more than a bright star. Even at the outermost reaches of the solar system, processes continue. The cold does not stop things from happening. It only slows them to a pace that requires patience to witness. Witness to its own light. A quasar is a galaxy in an early and violent phase, its central supermassive black hole consuming surrounding gas at a rate that releases more energy than the combined output of every star in the Milky Way, focused into a region no larger than our solar system. The light from the brightest quasars can be detected across most of the observable universe, their signals having traveled for billions of years to reach our telescopes. When we observe a quasar, we are seeing a galaxy as it appeared in its youth, turbulent, brilliant, feeding hungrily on the dense gas that surrounded early galactic centers before star formation had consumed or dispersed it. Most large galaxies, including our own Milky Way, are thought to have passed through a quasar phase in their early histories. The supermassive black hole at the Milky Way's center, Sagittarius A*, 4 million solar masses, currently quiet, may once have been a quasar, blazing across the young universe before its fuel was spent, and it settled into the relative stillness it maintains today. What looks dormant now was once one of the most luminous things in the cosmos. Quiet is not the same as always having been quiet. Quietly, the oldest stars in the universe have been burning since before the Milky Way had its current form, and their light is information about a time we cannot otherwise access. Population 2 stars, metal-poor and ancient, formed from the second generation of cosmic material gas that had been enriched by the deaths of the very first stars, but still contained only trace amounts of heavy elements. Their spectra carry this history. The ratios of elements in their atmospheres record the conditions of the interstellar medium at the time of their formation, preserving a chemical snapshot of the young universe. By reading these spectra carefully, astronomers can reconstruct what the galaxy looked like billions of years ago. What elements were present, in what abundances, in what configurations. The stars themselves have aged. Their surfaces cooled from their original temperature, but they carry their formation chemistry with them, like a diary written at birth and never altered. The oldest things in the galaxy remember its earliest conditions in a language written in atomic transitions, readable across any distance by anyone with a spectrograph and enough patience. Patience is what the universe practices most fluently in the way galaxies grow, merger by merger, across billions of years. A large galaxy like the Milky Way did not form all at once from a single collapsing cloud. It assembled gradually, accreting smaller galaxies and star clusters, pulling in streams of gas along the cosmic web's filaments, growing through a process called hierarchical structure formation, in which small things combine to make larger things, which combine to make larger things still. Evidence of this history is written in the Milky Way's stellar populations, streams of stars with similar ages, compositions, and orbital properties that betray their origins as separate galaxies, now dissolved into the larger structure. Every star that formed in a galaxy the Milky Way consumed billions of years ago is still here, still orbiting, still carrying in its composition the record of where it came from. The galaxy remembers everything it has ever absorbed. It holds its history in its stars. Stars that emit, in their dying, the particles that pass through you now. Every second, approximately 65 billion neutrinos from the Sun pass through every square centimeter of your body, through the blanket above you, through the mattress beneath you, through the floor, through the Earth itself, and out the other side. They do this day and night, regardless of whether you are facing the Sun, because the Earth is as transparent to them as a pane of glass is to visible light. These solar neutrinos are produced in the nuclear reactions at the Sun's core, each fusion event releasing not just energy, but a neutrino that travels outward at nearly the speed of light, escaping the Sun in about 2 seconds, crossing the distance to Earth in roughly 8 minutes, and passing through your body without interacting with a single atom. You are being passed through, constantly, by messengers from the Sun's core, from the very center of the fusion process that makes life on Earth possible. The Sun's heart reaches you not just as light and warmth, but as a continuous stream of nearly massless particles that treat your entire body as though it were made of open space, which, as we established some time ago, it mostly is. Mostly made of things we can account for, and yet the universe is ordinary matter. All the atoms, all the stars, all the gas and dust and planets and people amounts to only about 5% of the universe's total content. The rest is dark matter and dark energy, invisible, undetected in any direct sense, known only through their effects. 5%. Everything you have ever seen, touched, or measured, every galaxy in every deep field image, every atom in every organism that has ever lived on Earth, is 5% of what is there. The other 95% moves through the universe, doing its work holding galaxies together, accelerating expansion, shaping the large-scale structure without ever showing itself to any instrument we have yet built. This is not a failure of science. It is an honest accounting, a recognition that the universe is not obligated to be mostly made of what we can see, and that the visible is not the measure of the real. We have mapped 5% of the cosmos in extraordinary detail. The rest waits, patient and enormous, for tools and ideas that do not yet exist. The universe is not nearly finished being understood. Understood partially, approached carefully the way astronomers approach galaxy ages, reading light that left its source billions of years ago, and asking it questions it did not know it was carrying. The spectra of distant galaxies reveal their stellar populations, the distribution of stellar masses, temperatures, and ages from which the overall age of the galaxy can be estimated. Some of the most distant galaxies observed by the James Webb Space Telescope appear surprisingly mature, more structured, more massive, more chemically enriched than the models of early galaxy formation predicted they should be. They are there, in the data, asking a quiet question about whether our understanding of how quickly galaxies assemble is complete, not overturning cosmology the foundations hold, but nudging, gently, at the details, suggesting that some processes operated faster or differently than current models capture. This is how science works at its frontier, not in dramatic reversals, but in persistent, patient anomalies that accumulate until someone finds the explanation that makes them make sense. The universe, observed carefully enough, always has something new to say. It has not finished telling us what it is, telling us, in the faintest signals, what the earliest galaxies were like. And those earliest galaxies are now coming into focus through instruments sensitive enough to catch light that left its source when the universe was only a few 100 million years old. What Webb and other telescopes are finding is a universe that assembled itself faster than expected galaxies, more massive, more structured, more chemically complex than models predicted for such an early epoch. The universe, it seems, was eager, not in any intentional sense, but in the sense that the conditions it established at the beginning were productive in ways we are still calibrating. The first galaxies ignited their stars quickly, enriched their gas quickly, grew their central black holes quickly, and in doing so, they changed the universe around them, ionizing the hydrogen that had made space opaque, clearing the cosmic fog, so that light could travel freely. They did not merely inhabit the universe, they transformed it. The first generation of cosmic structures rewrote the conditions for everything that followed, which means that every galaxy existing today, including the one you live in, including the star at its center that warms you, is downstream of those first urgent ancient beginnings that recede even further from reach as the universe expands. In the far future, not tomorrow, not in any timescale that touches human life, but in timescales the universe keeps casually, the galaxies, now visible beyond our local group, will one by one cross the cosmic horizon, their light redshifting to invisibility, their signals thinning below any threshold of detection. The universe will not end. It will simply become quieter, more separated, each island of gravitationally bound matter more alone than before. Stars will continue forming, for a while, but the rate will slow, the raw material consumed or dispersed, the stellar nurseries gradually emptying. In 100 trillion years, the last stars will exhaust their fuel and fade. What remains will be white dwarfs cooling toward black, neutron stars spinning slowly down, black holes evaporating over timescales so vast they make the current age of the universe seem like an intake of breath. And then, after all of that, after a silence longer than anything, even the black holes will be gone, and the universe will be a cold, still, nearly featureless expanse, expanding forever into a dark that has no further shore. This is not a sad story. It is simply the longest one, and we are in its most luminous chapter right now, tonight. Tonight, while the universe continues its patient work, neutrinos pass through the roof above you. Ancient photons cross this room. Gravitational waves compress and stretch the space between the atoms in your body by an amount so, and yet connecting this quiet moment to mergers that happened 1 billion years ago in galaxies whose names we do not know. The cosmos does not pause for sleep. It does not dim its activity for the night hours. Somewhere in the Milky Way right now, a cloud of cold gas is crossing the threshold into collapse. Somewhere, a massive star is in the last hours of its hydrogen supply, about to begin the sequence that ends in a supernova and the seeding of surrounding space with elements. Somewhere, 2 neutron stars are completing the last 1,000 orbits of a spiral that began millions of years ago, approaching the merger that will release a gravitational wave and possibly a burst of heavy elements, gold, platinum, the rarer metals flung outward into the interstellar medium to be gathered, eventually, into future worlds. Worlds like this one assembled from the debris of everything that came before, warmed by a middle-aged star, wrapped in an atmosphere thin enough to be traversed by starlight, thick enough to hold the weather that carries the water that fills the oceans, that once held the chemistry, that eventually, improbably, became alive. And life, once it arrived, did what life does. It grew more complex, more sensitive, more curious. It developed eyes that could detect individual photons. It developed minds that could construct mathematics precise enough to predict the existence of planets before they were seen, to calculate the expansion rate of the universe, to detect a vibration smaller than a proton and recognize it as the echo of a collision 1 billion light-years away. The universe made something that could look back at it, something that could lie quietly in the dark and wonder about the age of starlight, the temperature of space, the shape of what exists beyond the horizon. You are that something, not as metaphor, as fact. Fact held gently because the atoms in your body have existed, in various forms, since nearly the beginning of time. The hydrogen in you is almost as old as the universe itself. The heavier elements were forged in stars, and scattered in their deaths, and gathered again, and scattered again, and gathered again, across arrangement in this particular body, on this particular night. You have not always been you, but you have always been something. The matter that composes you has never not existed. It has simply been other things: plasma in a stellar core, gas in an interstellar cloud, ice on the surface of a comet, mineral in the crust of the early Earth, salt in an ancient ocean, carbon in a living cell. And then, through a series of events that defies simple summary, you. The universe did not make you deliberately, but it made you inevitably through the patient accumulation of conditions that were always, given enough time, going to produce something like this. Something warm and soft and capable of knowing it is here. Here, in a galaxy that is itself part of something larger, which is part of something larger still, nested structures of matter and gravity and time, extending outward in every direction to scales that language reaches toward and never quite grasps. And all of it, from the quantum foam seething in the space between your atoms to the filaments of dark matter stretching across hundreds of millions of light years, all of it is operating right now, in this moment, while you breathe. The universe does not have an off switch. It does not rest, but you can rest inside it, held by a planet, held by a star, held by a galaxy, held by a supercluster, held by a web of dark matter, older than any star. A series of embraces so vast and so quiet that the mind, given enough stillness, can begin to feel them, not as weight, as support. The universe is not indifferent to you in a cold way. It simply operates on scales that dwarf personal concern. And in that dwarfing, there is a kind of relief, the relief of being small enough that the largest things have no argument with you. The cosmos holds no grievance. It simply continues, immense and ancient, and you are briefly, beautifully, improbably within it. Within it as you drift now, if you are drifting, if the voice has carried you far enough from the day that the day feels distant, if the thoughts that were sharp when you arrived here have softened into something less insistent. The universe has been at this for nearly 14 billion years. It is not in a hurry, and neither are you. Right now, in this moment, in this body that is mostly empty space, arranged into the pattern of a person resting. Your breath moves in and out a rhythm older than you are, older than your species, a biological inheritance from organisms that breathed in ancient seas before anything had yet walked on land. The air entering your lungs contains oxygen made in the cores of stars. It contains nitrogen that has cycled through this atmosphere for billions of years. Every breath is an exchange with a system so large and so old that your participation in it tonight is just one breath in a conversation that began before the Earth existed, and continues out past the window, past the clouds, past the thin blue atmosphere that holds the weather and carries the birds, out into the dark where the moon is moving through its orbit right now, one fingernail's width further from Earth than it was a year ago, and the planets are turning in their paths, and the sun is fusing 4 million tons of itself into light every second, and the nearest star is 4 light-years away in a silence so complete that no instrument we have ever built can adequately represent it. And beyond that, star are hundreds of billions more, and beyond the galaxy are hundreds of billions of other galaxies. And in the space between them, ancient photons are crossing distances that have been expanding since before the Earth formed. And somewhere in the cold dark between the stars, a molecular cloud is beginning, very slowly, to collapse, and somewhere, a white dwarf is cooling by a fraction of a degree, in a process that will take longer than the current age of the universe to complete. And all of this is happening at the same time right now, in the same moment as this breath, and this one, and this one. The universe is not waiting for anything. It is simply being what it is, everywhere at once, in the vast and patient and luminous way it has always been here, and you have always been part of it. The boundary between you and the cosmos is less solid than it seems. The air you exhale becomes the air someone else inhales. The water in you will eventually return to the ocean, evaporate, fall as rain, run in rivers, gather in ice, melt, and flow again. The atoms in your body will outlast you by billions of years, passing through future stars, future worlds, future arrangements of matter that we cannot imagine. You are not separate from the universe and then placed inside it. You are continuous with it, a local concentration of its oldest materials, organized into a form that can feel warmth, hear sound, notice the quality of silence, and choose, on a particular night, to lie still and let the enormity of everything be a comfort rather than a weight. That choice to let the vast be gentle is available to you right now, in this moment, as the cosmos continues its quiet work in every direction at once, and you are held, without effort, at the center of your own small and sufficient world. World growing quieter now. The facts have settled. The numbers have dissolved back into feeling. What remains is simpler, the warmth of wherever you are, the rhythm of your breathing, the particular darkness behind your closed eyes, that is yours and no one else's. Out past the walls, the night continues. Stars are crossing the sky in their slow arcs, carried by Earth's rotation, not moving themselves, but appearing to move. A reminder that all motion is relative, that stillness and motion are always defined by where you are standing. And you are not standing anywhere. You are lying down, releasing the day, releasing the need to understand or resolve or complete. The cosmos does not require your attention to function. It will continue its patient unfolding whether you watch or not. And tonight, you do not need to watch. You can simply be inside it, one warm, breathing, temporary arrangement of ancient matter, resting in the dark on a pale blue world, while the universe does what it has always done, continues, quietly, in every direction, without end, and without urgency. Let your body be heavy now. Let the thoughts that remain grow soft at their edges, less defined, more like weather than like words. Somewhere above you, past the ceiling, past the clouds, a satellite is crossing the sky in its orbit, tracing a line of reflected sunlight across the dark. Past it, the moon. Past the moon, the sun on the other side of the earth, already warming tomorrow somewhere else. Past the sun, the planets in their patient ellipses. Past the planets, the long, cold silence of the outer solar system, where comets drift on journeys measured in centuries. Past that, the nearest stars, each one a sun, each one surrounded by its own dark and its own possibilities. And past them, the galaxy, turning. And past the galaxy, the local group. And past that, the filaments. And past that, the horizon, that quiet boundary, where the known gives way to the unknown, where light has not yet had time to arrive, where the universe keeps its oldest secrets in a dark that is not empty, but simply, for now, beyond reach, and somehow close. Because all of it is made of the same thing you are made of. All of it follows the same laws that govern the atoms in your hands. The universe is not foreign to you. It is, in the most precise sense available, what you are made of, and what you are inside of, and what you are continuous with, in every direction, without exception. You did not arrive here from somewhere else. You arose here, From the same plasma and gravity and time that made the stars. And tonight, you return to something like that original simplicity. Warmth, darkness, rhythm, rest, the mind quieting, the body releasing, the long day becoming the long night, which will become the morning, which will come in its own time, without being hurried. Let it come in its own time. For now, this is enough. The stars are where they are. The universe is doing what it does. And you are here warm, breathing, real, held by a planet that has been holding things like you for hundreds of millions of years, and has not once let go. Sleep is close now. Let it find you. The cosmos will still be here when you wake. All of it, every galaxy, every ancient photon, every dark matter filament, every star being born right now in a cloud of cold gas, somewhere in the spiral arm of a galaxy you will never visit. All of it will be here, patient and vast, and quietly ongoing. When you open your eyes again, you don't have to hold any of it. It holds itself, and it holds you. I hope you sleep well and dream softly. Good night.